All right, let's talk about vector fields. So, how's everybody doing today? Vector fields, what are they? They, in fact, will combine the features of vector functions that we've discussed. Of those we discussed, of course, depended on only on a single parameter, and scalar functions, where one function depended on 2 variables or maybe 3 variables, maybe even more, up to imagination, in which we could interpret as the scalar function of the vector input. Now we'll combine the two together. So let's start with the simple illustration of the concept, how it appears naturally. So let's look at the situation where we are looking at directions of wind and magnitudes around the Golden Gate Bridge. So we can record at different times of the day. Of course, they will change drastically. So left one records the one taken at 6 p.m. and another 12 hours earlier at 6 a.m. on the same day. So rather than using longer arrows for larger vectors, they're using the fat or different colored arrows. So of course you can see that the strongest winds are first on the left. You can see they're going around the Golden Gate Bridge, and on the right in the early morning, maybe somewhere around Mount Diablo. Similar patterns you can see if you look at the fluid velocities, say of the coast of northeastern Canada, or around an airflow, around an airfoil and a wind tunnel. At each point, you can stick a vector which describes the motion of the, especially if the process is stable, when it doesn't change with time, it will show you the stable flow of either water or maybe air, etc. So then, since we are associating such a vector at every point, then we have what's called a vector field. So if it's on a plane, like all the examples that we've seen before, that is a vector which depends on the position in the plane on 2 coordinates, x and y. And it may be defined on the whole of R2 or maybe only on a particular region in R2. So then at each point you have a vector sticking out. So we will, rather than placing it in the origin like we like to do before, we will place a vector at the point to which it corresponds. So at each x comma y, at each point on the plane, we will have the vector placed like that. So if we write its components as p of xy and q of xy, then of course we will have the 2 scalar functions, p and q, as functions of x and y. So we can kind of reduce the situation to just dealing with 2 scalar functions of 2 variables, x and y. Or we can instead write that we are dealing with, we can associate x, y with the vector x. And we can have written it like that, p of x comma q of x, functions of a vector input, or even f as a function of a vector input. So we get a vector input, and this function gives us the vector output from vectors to vectors. So far, for scalar functions, we had vector inputs but scalar outputs, and for vector, for curves, for vector functions, we had scalar inputs and vector outputs. Now we combine the two, we get both vector inputs and vector outputs in this case. So that's what we call a vector field. Good. So similarly, we can imagine the same animal in 3 dimensions. So then, depending on 3 inputs, x, y, and z, we will get a vector. So again, 3 scalar outputs, 3 components, p, q, and r, traditionally denoted like that. Okay, so if if you thinking of something plain, then you can think of maybe a hedgehog with needles sticking out in all directions. And in 3D, maybe think of this blowfish, or whatever best analogy you can think about. All right, so that's what they are. Let's try to work with them. So let's give a particular vector function, two-dimensional vectors taken to two-dimensional vectors like that. Let's try to understand how it looks like. How can we graph it? So let's plot this vector function of vector field. Sometimes we'll say vector field. There's a bunch of vectors on the plane. So minus yx. So we plotted a few here, maybe 5 different ones. Doesn't make it clear what exactly it represents. So let's be a little bit more systematic and plot a few like that with what is common in between these two. That we are trying to keep the points x, y same distance from the origin. So for instance, here they are all distance 1 on the unit circle. So it appears that this vector field is indeed tangent to at least to the unit circle. So is that always the case? Let's see. Here we plot a few more. Maybe it's a good idea to go and plot a few more, and then we'll try and check, do they really appear always tangent to some circle? So can we draw a circle so that it's always tangent to? So let's see, if we have that as a position point on the circle with radius r, so radius of the circle is of course square root of x squared plus y squared, then if it were tangent to that circle, then there would be 90 degrees angle with the radius. So to check if the angle is indeed 90 degrees, we will do the scalar product of the vectors minus y comma x, the f vector, and vector with coordinates x, y, or x, a position vector of the point, coordinates x, y. So let's see what happens here. We'll have x times negative y plus y times x. What do we get? Of course, 0, because they cancel. So indeed, there would be 90-degree angle, and there would be perpendicular. In other words, the f vector is always going to point along the tangent line to the circle. So that would be a vector tangent to the circle determined by the position point. Good. Okay, so we understand this vector field now. The magnitude, by the way, will be exactly equal to the radius of the circle. Look at the calculation here. All right, so some other examples. Of course, most of this will come from physics, very useful concept in physics, which describes the force field. Mostly it's for force fields or for velocity of flows. So for fields given by velocities of flow of a liquid or wind velocities, etc., etc. So let's imagine the steady velocity field of a fluid in a pipe. So then at each point you have the velocity of the fluid. You can imagine the vector sticking out at every point. So that would be everywhere inside the pipe. So the domain of the definition is interior of the pipe. Here they are going like that. That's another example. Maybe the one that we looked at, negative yx is f, could be a counterclockwise rotation of the wheel. The velocities that we observe on the counterclockwise rotation of the wheel. Then, of course, forces. So here's the gravity force, one of those inverse square laws. Then we know it's always a force of attraction, so between the two bodies. Hence, when we write it as a vector, so that's the magnitude of that, but what's the vector? Well, vector would be the, if the position is the vector r, or position vector of the point with coordinates x, y, z in 3D, if the center of mass is at the center of something like a sun, or the more massive body, then we will have the minus here, minus mg divided by r cubed times r, so that we would get the unit vector opposite to the position vector. So we can keep original r squared, and here we have r over r magnitude, that is the unit vector in that direction. All right, so gravitational force is one such example. Another, of course, is electrostatic force. Here we are. So maybe one more word about gravitational force, which we said is this, is if we imagine the vector of gravitational force associated to any point in the space, then we're talking about gravitational field. So if we place like a probe mass m, what would be the force acting on this probe mass? That would be exactly that expression, and we'll have the vector field for gravitational field at any point in space. That's how it would look like, written in components. Not so trivial if you remember that r is square root of x squared plus y squared plus z squared. Of course, why on the outskirts the vectors are getting small? Because we said it's the inverse square law. They are getting small, inversely proportional to the distance from the origin, to the square of the distance from the origin. Very similar law acts for electrostatic charges. So that's the electrostatic force between the two charges. Again, put a large charge Q in the origin of our coordinate system. Then the other small q will be acted upon. Now there is a choice between the attraction and the repelling force. So they will repel if q and both charges have the same sign. So the product is positive, both positive or both negative. Then the force will be that of will be a repelling force. And if they are negative of each other, the opposite charges, then will be force of attraction. So this example of force fields for gravity as well as the electrostatic charge we also may divide by the mass or divide by the charge to get the force per unit of charge, and that will be known as the electrostatic field. And we can electric or electrostatic field of the main charge Q or main mass M at the origin, and we can graph that instead. Okay, so gradient fields are special ones satisfying this equation for some f, for some scalar function f. Because starting with a scalar function, gradient f will produce you the vector with three components, dxf, dyf, if you're talking about the function of three variables, dzf. But we'll talk about that in class. All right, see you then.